welcome you to the final talk of our seminar series, which is the spring of 2025. So we have now, every semester, we have 4 speakers who discuss and share their research or their work on very diverse topics. So we like to also keep it very broadly focused, so that, or I would say broadly set, so that it reaches a diverse audience that we work with in the Design++ community. So this year we had 4 great speakers, and if you haven't had a chance to join live, you can also visit our YouTube channel where we archive all of our talks, and I think we have talks from 2020 as well, so from then until now. So this has been running since then. Feel free to check out the archive. I know last week I couldn't make a talk and I really want to see it. So it'll be online very soon. And so before I introduce Anton, I want to ask, the seminar series is also a part of a one credit master's course or master PhD course. Can I ask, who are the students from the course? Can you raise your hand? Okay, this has generated more students who attend this lecture, so thank you for attending. And so now I will introduce Anton. So it is a pleasure to introduce Anton. He's a colleague of mine here in Design++. And just to give you a bit of a background, Anton is an architect and also a postdoctoral researcher at the Digital Building Technologies team with Benjamin Dillenburger. He originally joined ETH to work on the project of the 7-day house. And so that's how we had the first interactions with Anton. And that is also incorporated as it's a Design++ project. So, and since last year, I've had the pleasure and opportunity to work with Anton on so he is the Deputy Executive Director of Design++, and so we work together also to lead the initiative. But Anton not only does that, he does a lot of research, and that's what you're going to hear about today. So working on large language models, but also generative AI and foundation models, and how that is applied in architecture. So without further ado, I'd really like to hand it over to you and look forward to your talk on architecture and machine intelligence. Thanks.
Thank you. Cool. So welcome. It always feels at home to present to known faces, but I'm always nervous. And I think I've given a version of that talk already, and still I'm nervous because it's the way I see these talks. For me, I always approach them that I want to share where I am, to be really sharing work in progress, so we can have discussion. We can kind of have a critical moment of critical thinking, and this is what moves forward every one of us. So yeah, that's also adding to this nervousness today. So, it's great to present in front of a known crowd, right? It's really nice. I want to start today the topic of architectural machine intelligence with the magic of architecture, which happens in synthesizing material, functional, cultural, and aesthetic influences into a coherent design, a vision for what the world can be. So technology has often required us architects to turn it into an explicit logic. This is what happens by intuition, almost inexplicably, so we don't know how it appears. And every technological paradigm so far has been like this, from the modernism and industrialization, the parametric design period, digital fabrication, which we are very well familiar here with, performance-driven sustainable design. Everything required us to explicitly state something that doesn't happen with an explicit way. So my main argument here today is that architecture's historic love and hate relationship with technology is giving way to this new paradigm. Machine intelligence that is capable of translating the architect's fuzzy, intuitive, and explicit intent into an explicit design logic without forcing us to sacrifice our human agency. And this is also something I like to do in the beginning of talks. I have 105 slides for you. I think 3 are important. I need the rest to communicate those 3 well. So let's see if we agree on which those 3 slides are. The numbers will be here if you want to note them down. So this is a question that's now almost outdated, but who here uses a chatbot at least once a week? Let's see. Yeah, everyone, right? It's outdated. It's like who owns a smartphone almost, and it's been only 3 years. And how about Midjourney or other kind of text-to-image to generate architectural renderings? Yeah, slightly less, but the architect crowd at least. So many, right? Many of us. And there are many scenarios in which one would use one. But we don't often admit it. And I think it's understandable. Because in a way, we might consider it a form of weakness to outsource intellectual work to a machine. Because we grew up in a world like that. But it's not the same with the upcoming generation. I have my kids here today, so they count also towards that. But more importantly, the thing I want to mention up here is that last year in November, together with Design++ and NCCR DFAB, we gave a workshop as part of the Nationale Zukunftstag for 14-year-olds. And I gave a small workshop on image generation. And when I asked, what do you know about AI? Everybody raised their hand. And they said, ChatGPT is for homework, ChatGPT is for image generation, ChatGPT for hobby. So all of them knew, they worked with this tool. And this ChatGPT generation, 14-year-olds, in 5 years will start their studies in university. They will also, some of them will come to study architecture here with us or with whoever is here. I think that's a very important thing to consider, how this thing is changing. And more artificial, more precisely, I'd like to call it machine intelligence, because everything is artificial and everything is natural. Machine intelligence is already making an impact in multiple important fields, most notable in medicine recently, won a Nobel Prize in chemistry. But what can it do for us, right? And this is moving so fast that in many ways we can only kind of envision much work is still out to be done. So before we look at what might be possible, we need to, I think it's very important also to appreciate what we as architects are actually doing, like what this multidimensional human artificial intelligence is. So I looked, as part of research I'm doing, I looked at the literature on design cognition, also more books than listed here, but we looked at that, and it's kind of a work in progress framework for the dimensions of human architectural intelligence. So we can think that architects excel at perceiving, representing, and manipulating geometry and spatial relationships. It's kind of a given. Architects also understand construction techniques, material properties, and regulatory frameworks. We possess a nuanced awareness of the artificially and collectively created shared realities, right? This is what our discipline creates culture. And how the built environment influences the human experience. Also, we are very well capable in addressing complex, these wicked problems, ill-defined problems that are characterized by incomplete data and conflicting constraints, so developing holistic solutions under uncertainty. Architects also learn about design problems by trying solutions rather than exhaustively analyzing the problem. There's no method. There's no explicit way of doing it. And then we embrace this open-ended process as a catalyst of creativity. And then architects also ensure that projects align with the shared values of the stakeholders, frame innovative solutions, communicating effectively. So it's not always about solving something in architecture, but sometimes it's about pointing to a point that does not exist, to a world that we could inhabit and create it. And of course, every architect is influenced by personal intuition, aesthetic appreciation, and prior experience, which enables serendipitous discoveries. So I think that the state-of-the-art computational design and digital fabrication techniques helped us really augment 1 and 2 here. And this is what all of us here at ETH, NCCRD, Fab, Design++, in this network, we are all familiar with that, and we are experts in it. And each one of us has mastered the technique or created their own tool into turning their own intent into a computational logic. It's a little bit of a stretch, but the argument here is that agentic AI, as it emerges now, as it exists now, and where it's going, enabled by foundation models, have the potential to do 3 up to partially 6. And a truly general architectural machine intelligence needs to have some capacity to do at least all 6, right? So this is how I think like the starting point from human intelligence moving to machine intelligence. So let's look at how architectural machine intelligence is evolving. It's my take, also my own path through that. And we started, and that's what we've worked with, right? We know the world of 1,000 variations, where you create a parametric model and you can explore its design space. Here's a simple example with a generative system that's based on the marching cubes algorithm coming out from a master thesis I supervised during my PhD in Darmstadt. So the user can sculpt, it's an interactive thing, can sculpt the building, and the algorithm kind of places all the right elements, so it completes, it's always kind of looking like a complete design. Here's another one from a colleague at the chair of Digital Building Technologies, Hang. He's also here. We can ask him later more about that. I have a pleasure of working with him. It's called Mask Plan. We published it last year at CVPR, and it's learning data from floor plans, given a boundary condition and partially defined layout attributes, like which rooms you want, what kind of connectivity you want between them, sizes, locations. It auto-completes this and generates a layout. So a lot of variations to be explored here. And usually the way to make this, to connect this paradigm of the 1,000 variations, these computational tools, to connect them to the other aspects, other dimensions of architectural intelligence, was to make them interactive for the architect or for other stakeholders, so that we can tap into the way we perceive and experiment with the design we have in front of us. Then what you see here is an immersive interaction project we supervised together with Wen from DBT. It's within a mixed reality course offered at the computer science department, where we used scaled 3D printed furniture models as interactive markers to determine which of the rooms where you want them, to define the size, and then the floor plan basically is generated. So you can play with that and kind of think and reflect on views, think and reflect on how you want this layout to be. But one thing that is really a problem with this paradigm of 1,000 variations is the so-called bitter lesson that Rich Sutton formulated, which states that general methods that scale with data and compute, such as search and learning, will in the long run outperform approaches that rely on the human knowledge and domain-specific insights. And this computational design tooling is relying on human knowledge and domain-specific insights. So we can learn a lot from a vast amount of data. That's the message here. But what does it give us, right? And then we come into this next paradigm, into the world of countless fuzzy options. To understand what it really means, I think that's also the realm of machine learning models and lately of foundation models. So let's look at a foundation model definition, just so we are all on the same page. So a foundation model is any model that is trained on broad data and generally using self-supervision at scale that can be adapted or fine-tuned, for example, to a wide range of downstream tasks. It's a very big shift of how we've worked until now, right? Because usually we have our own data, we build our own model, and we apply it at the problem we have. Now suddenly, there is this huge amount of data, and it's a huge model that is taking millions of dollars to train and also a huge amount of time to train. the data that's needed to train GPT-4 is petabyte, 1 petabyte. So it's impossible for any one single one of us to train such a model, but the quality of it is generalizable, right? It can be adapted for a large amount of downstream tasks. And this adaptation is what is very interesting for us. At the beginning, just using the models, but also using them to create embodied agents into environments. I think I'm always kind of excited to show this because to understand also how this world of fuzzy options works is basically computer scientists have figured out a way to do math with concepts here. For example, we have the embeddings of various concepts such as cities, travel, food, body parts, feelings, relatives. And then what you can do in that vector space of embeddings is you can take the point where Paris lies, subtract the point or the vector which represents France, add the vector of Poland, and you land nearby Warsaw. So you can do really math with these concepts. Or Japan minus sushi plus Germany equals bratwurst. So a country and its famous food plus another country then gives you the famous food of that other country. And this is how this space is navigated. There is no precise end, right? There's no precise states in that. Everything is continuous. Works the same with images. So math with images, here we have from the now famous paper on CLIP, 2 images that we are working with. Right at the center on a path that connects them is this image, and along that path are these images. And then if you take a different route, then you have a different way to sample. So you can sample that space at any moment, and you always get something. Is that well-defined? Is that not so well-defined? What is also interesting is that at the moment, these techniques are applied to representations such as protein molecules. So what would be the architectural representation that is not an image, that is not text, right? We don't work always with these concepts, so they're not enough for what we work with. So it's something to think. So this math with concepts and math with images, roughly, I'm oversimplifying here, gives us these 2 best scalar architectures of foundation models today, the transformer models and the diffusion models. And scalable means that, you add more data, you add more computing, and then you get more emergent capabilities, more generalizable capabilities, more downstream tasks on which you can apply it. So let's look a little bit at, I think it's very good to also appreciate, for example, in diffusion models, how quickly all happened. So here's the evolution of text-to-image models. And then we'll be looking with a prompt of a cross-generational housing cooperative building with organic living walls, something that is not present in the training data, for sure, doesn't exist. So the very first version of DALE, the first text-to-image model, gave us this floor plan. And the very first version of Midjourney gives us this perspective. So that's, 4 years ago for DALE and 3 years ago for Midjourney. 2 years later, after this moment, this is the floor plan that DALE can give us, right? And this is the visualization that Midjourney can give us. So again, this is what was possible at the very beginning of the release. And this is 2 years later, or 1.5 years later. Big difference, right? They kind of plateaued there, but I think already as a sheer kind of speedy development that we have not really fully embraced yet, quite important to consider. And this progress has moved also to video. Here is an experiment I briefly did with the OpenAI video model Sora, where I generated this image with Midjourney. That's the starting image. And the prompt is architects working on a model. Here's the video. So the video model kind of suggests what's on the side of this, what is behind it, knows about the spatial relationships of touching the model, being around it, and simulates all this. A lot of things to explore here. Here's another example of a project I'll show later. The starting image is from a project I'll show later. And then the idea was the prompt was to start with that image and show a residential building in the twilight. So it's like I'm saying, it's a lot of fuzzy options. And then people were trying to figure out, okay, what's the way to bring architectural control, a little bit more architectural systematics into the things we're generating with these. And control nets were used for this kind of experiment here, which we did together with, it's a demo for the IDL, which we did together with Wen from DBT. So all starts with a very basic parametric model of a tower, which you will see in a second, which is just a blue box that's traveling in a skeleton of columns and beams. And then some of these cells are empty and some are full. And if you share a guiding image, if you use a guiding image to guide the control net with, and pass it that skeleton information, then it will generate the images of the high rises that you saw. If you change the position of the box, we did that using the OptiTrack here. So you're kind of pointing as with the bow. You can change the position of the box. If you pull the bow, the box becomes bigger or smaller. Then that's how you can control. Then the guiding image guides the image that you render out of it, so AI rendering. But even with this control net, right, it's not enough, because a design may start with an image or maybe communicated with an image, but it's not an image. It's not text, it's not image. And this world of fuzziness is not everything that we would need. So these are projects I worked on while at the computational design unit at Bollinger+Grohmann, and they show this hierarchy of rules, the material properties that you need to consider, how things are joined, how you assemble them, how you test that they will structurally stand, how you test that they can be actually constructed, and to create the space of the image that you want. So this neural network-based computation is too fuzzy for that. And tying all these hierarchical dependencies that I mentioned before across manufacturing, supply chain, and assembly is what the 7-day house project that Danielle mentioned was the reason for me to come to the ETH a couple of years ago, and that I'm working on with Professor Dillenburger and Professor Hall on. So we looked at that hierarchical dependency there, and the idea is to generate an algorithm for rooftop extensions that takes into account the specific building product that we will use for the detailing, and also generates a layout, quickly customizable layout, so that architect or inhabitant can customize it. And then when you're ready to go, you just say 7 days manufacture and delivery. Here's a workshop that we did with students last autumn. Yeah, music from my laptop. So one thing that we noticed in that workshop is that we gave them a set of tools that operated on one given logic of how you generate designs with it. And students could, the first thing that every team did is break the system, right? No, this logic does not work for the ideas we have. And that was also a great learning, but it was also a very creative moment, because suddenly 4 or 5 more logics appeared that one could consider of how to design with the system. But let's first look at the principles behind it. Then we'll talk about this kind of idea to deviate into different logics of forming a layout. So the challenge, right, the main challenge in the 7-day house is how do we create a methodology that is capable of adapting to this inevitably different details of various suppliers. This is the same moment of a building from 2 CLT producers. One is KLH, the other one Stora Enso. So you see that the detailing, if you spend a little bit of time, you'll definitely see that the detailing is different. And then working with our partners from ERNE, we basically learned that it's a very rule-based system when you, or approach when you look at the level of the building elements. If this, then that, right? So products such as slabs, walls, and roof panels are placed based on the space adjacency. What category of space we have on the two sides of that wall or on that slab. Is it something that requires sound insulation? Does it require wet proofing, and so on? So basically, you can very quickly create a matrix of interior, exterior spaces, interior wet, interior dry, interior soundproofed, exterior also terrace, and so on. And then create the minimum amount of details, or the element-to-element relationship, so that you can also standardize this and use it in the generative algorithm to always know, based on the rooms that your algorithm places, that the algorithm places here, that every single surface is labeled with, that's the product we're gonna require from the supply chain to first manufacture and then deliver. And this kind of, that I mentioned, this strict logic on an element-to-element basic, that's what stayed in the student projects, but the logic of creating the layout, the logic of creating the house changed, and here's why. Even though at the level of the elements, the rules are there, there's no rule for a design logic that can work for 1,500 different rooftops. In the context, for example, of urban densification, adaptive reuse, and these 1,500 are just a fraction of the reality that we're dealing with, but still no single design logic or concept can address all of these. So a method that produces logic might, right? That's what we're looking for here. Can we augment our thinking into, how do I approach a thin rooftop that is exposed to east and west? How do I approach a kind of a bulky building that is exposed north-south? Central vertical core or linear vertical core. All of this requires different way of thinking. Good views, bad views, right? Also requires different way of thinking. And then, so by now I really hope that I have been able to communicate that this old kind of school computational design gives us really precision that we need, but lacks the generalization, and the foundation models, image generation and language models, can scale on generalization, but are not grounded in the documents that we architects use to make sure that a building has a clear compositional organizational principle, but can also be functional and can stand. So the idea is, how can we bring these together? And this is where we enter the world of agentic AI. Just a couple of ideas of where language models stand today, so that we understand also the capabilities that they have that enable agentic AI. So recently, LLMs have surpassed the human baselines for many multi-subject benchmarks. We'll come to benchmarks later, though, offering a computational form of general knowledge. We see that here, that these creeping up lines of all the different models taking tests. And LLMs are also can simulate human behavior quite well, which leads to this open-ended reasoning, or at least what appears to be reasoning. One of LLM's greatest strengths that's very exciting for us doing research on this is that it can translate intent into the logic of making, which means that they can build tools and they can use tools through code. The two examples here. One is writing reward algorithms for training bots autonomously, and the other one discovers new skills in an environment that's the Minecraft environment of the game Minecraft, but still an environment that it doesn't know. And here is another one that LLMs can, while they lack architectural awareness, so to say, they can manipulate geometry. So you can see GPT is plotting a path through a maze just from the text description, and it's quite accurate. And here, it's the GPT version of Kandinsky. Basically, the shapes are there, but the spatial awareness not. Geometry can be manipulated. So bringing this together, right, the capabilities of guiding, planning, and turning intent into logic. And the need to have an environment in which to enact this logic brings us to this topic of System 1 thinking and System 2 thinking, which was made really famous by Daniel Kahneman, Thinking Fast and Slow, where System 1 is this intuitive, emotional way of thinking or approaching the next task, the next thing you do. And System 2 is the more kind of slow, deliberate approach, a more logical one. And this, in the computer science at the moment, is called neurosymbolic AI. So you have a neural model and a symbolic environment. This project really made it famous from DeepMind, where they were managing to solve Olympiad geometry problems without any human demonstration. So the LLM will plan how to solve it, and then it will code it into a mathematic symbolic engine to actually test whether that's solvable or not. But the two things really needed to be there in order to make this possible. So working on this research of LLMs and design synthesis at DBT together with Angela and Jeve, we were really wondering, could there be this alternative generative design paradigm that can engage with the open-ended architectural ideation using AI agents? So here's the first prototype we did. So if LLMs allow you to talk to anything, why not, talk to your design? So we created a very basic geometric environment where the LLM can use tools, creating spaces, connecting spaces, moving them around. And then based on a prompt, here it says, create an apartment for 4. It reasons, okay, what do I need? How do I plan this? Explains also the steps as it goes. And then it enacts option 1, option 2. You can also edit them later. We very quickly realized that there's no overarching organizing idea or organizing principles here. It just places rooms haphazardly. The rooms are properly dimensioned. They're maybe even properly connected, but it's just a chaos of a composition, a chaos of an approach to a design. So we really went back then to try the different neurosymbolic way of doing it. So if one agent is not enough, throw more agents at the problem, right? So agents everywhere. So we'll have 4 now. And in the next kind of work in progress, maybe even more. So we have first the design driver agent, which formulates a design intent in the form of a short phrase. Then the interpretation agent formulates a design task from it. And the modeling agent creates procedural 3D models through code, right? Build and use tools, what mentioned before. And then finally, we have an evaluation agent that assesses each model's alignment, each of these procedural models' alignment with the original intent and the architectural relevance. So this is kind of how it looked a little bit in every step. Here's the metaphor agent proposing a design driver agent proposing a metaphor, rippled a grid. Then it unpacks it into the language, the evocative language that, the formally evocative language that the metaphor contains. For example, here it implies structurally yet fluid spatial capacity and so on. And then the interpretation agent expands on this as if it's to delegate that to a designer, not knowing that the next step will be, again, an AI agent. So it really formulates a design task. Hey, here's how you can create an architectural concept model using that idea that was shared with us. A series of layer planes that expands and contracts. It's here in the text. But we do one task. Actually, we do 5 tasks for each of these design drivers, so that we come up with 5 different approaches, right? This is the generative power of language models here. It's not always the same way to approach it. Then this design task is given to the modeling agent, which pieces together a Python function using the Grasshopper Python API, so to say. We embodied it in Grasshopper so that if the script fails, it kind of reports its mistake. The language model tries to fix the mistake, gives a couple of tries until we have a successfully running script. And it generates 3D procedural models with clearly stated parameters. So they can be instantiated we ask the agent to instantiate it 5 times with just specifying different parameters. So this is what it looked like, some of the models. And we animated them through the parametric states. So you see that it's a continuous design space of that particular logic. Yeah, repeats. So what we found is that effective design drivers that are rich in formal interpretation generate better results, which really highlights this importance of high-quality input from us architects, which can formulate a design intent. And we also found that LLMs are really fantastic with coming up with diverse approaches to the same kind of design trigger. All of them are here based on one design driver. And then transforming this textual expression into from intent to explicit logic of making. A little bit more about the experiment. Using the framework, we started with 20 unique metaphors or design drivers here. Each was interpreted 5 different ways, so 100 design tasks. They were then given in different contexts of zero-shot, few-shot to the modeling agent. So we basically ended up with about 1,000 parametric models. And each of those, we asked the agent to give us 5 states. So those states were rendered, and we have 5,000 images to evaluate in the next step and see what the evaluation agent could give us and feedback. So when we look at that, as you can see here, the modeling agent provided only with a metaphor, so zero shot, just no design task. Does kind of a low average score, high degree of failure as well, so it is not really able to come up with a parametric model that works. Once we include the design tasks, the success rate improves, the score kind of slightly, but design task really guides the creation of the architectural models here. And then finally, the highest scores and success rates are reached when the modeling agent is also provided with previous examples of how this problem was handled, what kind of parametric models were created in previous prompts, where the success rate was the highest. Also, diversity of models were the highest, because we asked it, here's some example, don't do the same, try something different. And of course, for us, it was really important to also validate the language model, which is multimodal, right? And it contains a vision transformer. Can it actually serve as a reliable grader of quality? So on the left, what you can see in the 2 groups, there is the top scoring images on the bottom row. They really exhibit architecturally suggestive forms, higher complexity in geometry, and the low scoring ones, quite simple. You cannot even guess what the metaphor or the design driver was behind it. And then on the right here, on the box plot, it compares the scores of all images, all the 4,000, filtering the failed ones, and with images that was kind of handpicked by an architect, who did not know the scores that the images got, right? So they didn't know about each other's ratings here. And as you see that the handpicked images receive consistently higher scores, which confirms that there is this alignment with the agent's evaluation and the human's perception of the results. Here again, some of the top scoring ones, just rotating in their parametric beauty. You can read the paper here. You have a few seconds to scan the code, and otherwise reach out to me and you'll find it. But what I really want to give kind of as an important message here is that all this work, right, the process that we applied here with Angela and Gervais was our way of architectural thinking. And we were heavily influenced also by the reflective practitioner, which formulates a method how architects, or back to design cognition literature, how architects work by conversing with the situation, metaphorically. that you observe something and then you react. There's this constant conversational flow. And what I would like to ask you to do now is to imagine what AI agent framework you would want to devise that enhances your work. Because these agents, we can think of them, the agent of intent, the agent of method, or logic, the agent of creating something, and the agent of reflection. Maybe there is a missing one, or maybe you would put them in a different way, or maybe you don't need one of them. So I'll be interested to hear what you think of this kind of approaching architectural design. And another question that we had working on this is, where does actual architectural intelligence live today? Because how do architects understand buildings? How do they create designs? How they document their process? Used to live in these atlases, right? For example, the Durand's presses on the very left was an atlas of ready solutions for fragments of buildings. Unger's was a typological catalog here in the middle. And the Atlas of Novel Tectonics came with this idea of the paradigm of parametric design, and it was an atlas of processes. So what kind of atlas, I'm asking myself here, is emerging if we can map intent into logic? Is this atlas a machine, or is it something else? Yeah, how do we produce it, how we keep it, and how we can use it? And one other thing that we recently formulated, and it's still in formulation, so I'm happy to discuss about that, is that in all this work, right, we aim to augment every architect to excellence and not really replace the mediocre one. Imagine a world where all architects are replaced by a mediocrely capable AI. So we don't need architects, but the built environment is mediocrely created. I think it will be a horrible world. So let's aim for the top part of the sentence here, to augment everyone to excellency. And one thing to say, right, is that mediocrity can have multiple definitions. So I'm not here standing to define what it is, but you really get the idea of what I'm saying here. So this brings me, now that we have agents, that they can turn intent into logic, to this idea of machine agency, which is also very new. Algorithms acted upon our agency until now, and suddenly we can embody them in environments so they can act on our behalf and have an agency of their own. A recent publication on machine culture states how culture can be created, cultural artifacts can be created by machines. One, it says novel artifacts can be created from machines, right? That's something we looked at. Machines can then transmit and potentially mutate cultural artifacts in this process. And then C and D are about selection. So machines can select or filter between different artifacts created somehow, or humans can select between these diverse, culturally creative machines. Something to think about where we want to go as a discipline as well. What are we comfortable with accepting as a machine intelligence in all these processes? But what is also important is that we think as architects, and even though we say, oh, every architect thinks different and they never understand, we think quite similarly because we're humans. Machines think very differently. Especially in the recent kind of reasoning foundation models that show a lot of non-human strengths and weaknesses, it's very important to take a note of two very important ways of differences between human intelligence and machine intelligence. One is that machine intelligence produces different outcomes, right? If it's trained on examples, the model memorizes, so it produces what it's seen. But if it's trained on objective, which is reinforcement learning training, and the reasoning models we have today, they are trained also with reinforcement learning, just like AlphaGo was trained with reinforcement learning. So if it's trained on objectives, it can generalize across the rules and can make a surprising move, like this move 37 that was, 1 in 1,000, and actually no one even imagined it's going to be possible, but then won the game between AlphaGo and Lee Sedol. And the other difference is that machine intelligence not only produces different outcomes, but it produces them in a different way. For example, when you have a reasoning model kind of think in the moment of thinking before it actually produces an answer. Very often it might jump into different languages or some kind of gibberish because that's what it learned is most effective. So in a recent publication, they determined that if you force readability of the thinking process, of that thinking moment, basically the model performance degrades. So they need to think differently, or think, right? They need to work differently in order to produce good results that we will be okay with then in the final answer. By the way, the most upsetting thought that I read in one of my prompts started with, the user is apparently confused. After I asked it something, so I was thinking, okay, maybe I need to reflect a little bit better before asking. So these two differences, right, they can also give us a new understanding of architecture and new methods to work in architecture. I think this rather unsettling meme captures quite well the various differences and why they happen. You have the unsupervised learning that's trained on huge amounts of data, where we cannot even have the human capacity to peek into, that is producing all kinds of acceptable and unacceptable results, that is slowly being, with supervised fine-tuning, trained into something that kind of looks like a human, behaves like a human. And then finally, the cherry on top, the smiley face that we all actually interact with, is the reinforcement learning from human feedback. Now we have autonomous reinforcement learning emerging. But basically, we gain kind of acceptance in the different machine intelligence here, but we also lose some of the capacity or capabilities that are behind in that huge monster. And it's kind of coming also already to an end. What is interesting for me is that we know by now that computation can be used to create more effectively and more efficiently solutions to problems that we already know and we have solved before in a better way. I'm really excited that AI or different computational augmentation methods, architectural machine intelligence, can enable the discipline to solve unsolved problems, to innovate, venture into the unknown and discover novel solutions. But what I really want to bring here is kind of a new territory that's opening, right? Who creates this? Not only what we created, but who creates it if we have machine agency now and machine augmentation of human agency, where we go from the human experts that are already active, right? We're already using it, to everyone. So humans that are not experts, humans enabled by AI, and also autonomous or semi-autonomous AI agents. So in these quadrants here, right, that are now forming new, first we will have this kind of scale-up moment where this new AI-enabled actors create familiar stuff. I'm really excited about this one, the transform quadrant, where we have this radical change of the built environment by an AI-based society. I think that's where the biggest potential to unlock new opportunities for architecture is. And one that really requires a new mindset shift. Because unlike these previous design computation approaches, which dealt with the computable phenomena, quantifiable phenomena, parametric models, and so on, this new generation of AI is able to identify the qualitative patterns, to draw correlation between ideas, between the testing of different logics, and learn something from it. And every talk, like I said, is also sharing, open to kind of further contact, further collaboration, because all of it is very new, right? It's 4 years old, 3 years old, 2 years old. You cannot keep up. It's developing so fast that in the last week, there were 3 major announcements of new models. Lego GPT, by the way, came out today, so you can build Lego now, generate Lego models. So things are really happening fast, and we are kind of missing as a discipline there. We are really missing because computer science is driving this, and playful curiosity is driving this. So what is needed to unlock these opportunities for us, for architectural intelligence? What I would like to continue working on, and what I hope many of you will be inspired to continue working on. architecturally relevant benchmarks, right? I showed that there's a lot of benchmarking in the AI scene happening, but we don't know how to check if an architecture, what is architecture, right? How can we explain that? How can we test whether an AI-produced architecture that's worthy of a human architect? And the other thing is architecturally specific digital environments. And I'm not talking just the plain kind of CAD, BIM systems, parametric modeling systems. We need environments where AI agents can be embodied and that they're really crafted for architecture as well, for the way we work. Because the way we work is not through a language, it's not always through images, right? We sometimes sketch, sometimes we do a model, sometimes we do, this language of architecture is not yet accessible for artificial intelligence. So just very quickly about why benchmarks are important. You have 4,000 models being tested on the OpenLLM leaderboard on different benchmarks. None of them contains architecture. Because when you test them, here is a sample question, right? Who knows this building? Who is an architect and knows this building? It's this one, right? It's not even the full floor plan, but everybody knows it. It's this famous building by Corbusier. So I can test you, right, on that. But let's test an AI. So A is the section, correct? And B is of the same section, the 3 floor plans. So we ask it, I need to read here, which drawing represents a section of a building, A or B? So all of the models fail because they also argue why. They say, oh, the lower one contains a courtyard. The other one was revealing something about the interior connection. So they say the wrong answer. And one, I think, even says none. None is a section. Okay, so let's really give it a lot more information. So we can say, you know, image A is a section. Image B is the floor plans of 3 levels from a residential building, focusing on a fragment of 2 apartments. So everything is now stated. What is the function of the space labeled with 1, which is the street of the Corbusier, of the design that Corbusier made? None of them get it. It thinks it's a courtyard, mostly. I think that's the common answer. But look, if I say, change slightly the phrasing, if these are 3 levels from a well-known modernist, that's the phrase I added. The most capable model, or 1 or 3, gets it. Oh, this well-known modernist block. And then it even tells you it's the street. And you know, it tells you a little bit. But it's not because it is architecturally capable. It's because I did well-known modernist. And then it repeats what it learned from text training. Here is a depressing benchmark that exists. Can an LLM make 1 million on the real world? Can an AI architect make 1 million? Is that how we benchmark good architecture? I think we should avoid this moment, right? I'm saying as a discipline, we are missing a bit here. I think one way to approach this is this kind of interactive, task-based environments. Here's an example for web development. It's called MiniWob. So it contains 100 interactive web problems, and the agents can manipulate graphic, UI, and so on. But imagine, you know, can we come up with something where, what about editing a house layout, add a room, change the view of the bedroom to something else, or the creation of a facade design, or the choice of materials and products for a given building design. So these are tasks that we can maybe on a smaller bit, like I said. There are a lot of rule-based thinking in our discipline that when you look at the elements level. And the computational design techniques that I spoke before can be actually the beginning of shaping some kind of interactive parametric environment like this. So the other one, and almost last slides here, what is an embodied agent? So in robotics, there is this new environment that's called Cosmos, which makes use of, it's an NVIDIA product. NVIDIA development makes use of the Omniverse, which is another NVIDIA environment. And there you can really simulate physically accurate cars driving or robots manipulating objects. Maybe not what we need for architecture, but still we need this kind of architecturally specific geometric and simulation environment where we can embody and test these agents. And we basically need benchmarks and environments. I'm reminding again of these dimensions of architectural human intelligence. So we need these things in order to cover the whole spectrum, the dimensions of architectural intelligence. All the occupational skills that are tested for in many ways also at the university, in the practice, and so on. For example, can an AI complete a design studio project? How will it present it, right? What grade will it get? Can it be a part of a team? And so on. And I think also that our discipline is quite unique because inherently, again, we deal with these open-ended design challenges where the inputs are sparse, the data is really unstructured. We always complain about, oh, we don't have data sets. But actually, that's what architecture is. We will never have data sets. We should really embrace it. And every solution, every process is multimodal, and it fuses the spatial, aesthetics, and technical requirements. And I'm saying we should embrace it because arguably those are the very problems that the AI researchers are trying to work on when they're moving towards AGI. So many of the tame problems are solved, and models can generalize on them, but these are not yet the fuzzy environments. And so the way to look at this, today I kind of took you through this way I see architectural machine intelligence evolving. Also, it was my own path from the thousands of variations to the countless of fuzzy options and what I think today is the paradigm of these thousands of logics. And to kind of think how we can apply this, I just want to come to a final point about human agency that comes back to the coming generation of architects and professionals that will shape the built environment. So the young generation that comes into offices, I hear from friends, colleagues at architectural offices worldwide, they get these new hires and they tell them, we don't want to build. Why are we building? We should stop building. We need to do transformation projects. We need to work in a completely different way with the built environment than the way we have been working until now. Because this diagram shows it quite well, which is published 5 years ago. The anthropogenic mass on the Earth, the mass that we transformed from nature into built environment, has now surpassed the whole biomass, which is kind of steady with the green line here. And that's there. That's what we terraformed the planet. So do we keep transforming the nature into built environment, or can we stay with kind of this, slow down a bit and see how we can transform these materials, these buildings that already exist? And navigating this highly constrained and uncertain complexity of dealing with the existing and transforming the existing will require human intelligence, but also machine intelligence to really join forces. Because the focus of the discipline, again, is shifting from this producing unique one-offs, the space stations, the Guggenheims, the Sagrada Familias of the world, into the fat middle, as Daniel Davis frames it, where the self-similar, but yet always different new constructions and new renovations are. So I leave you with these 4 quadrants. I think this is a lot of opportunities that AI agents, AI machine architectural intelligence can enable. And we as a discipline, we need to kind of guide the way on this map to bring our own kind of capacities into the research that's happening and also the applications that will come. Thank you.
Wow, thank you very much for your great talk.
I think this can go into as one of the longest Design++ seminar series talks.
No, actually it was 50 minutes. So it was supposed to be 45 minutes, so it's 5 minutes longer. I would say it's not.
If you have any questions.
Yes. So I have a few questions from my side, but I would like to first open it up to the audience if you have any initial questions. Okay.
Oliver.
Thanks, Anton. I see sort of with all of these things really images, it's representations of architecture. and nothing yet that I've seen is really in a actual architecture, actual construction building. Is it about just getting to where we trust these systems enough to give them the reins of construction robots, or how do we make that step into building architecture, not just sort of?
Yeah, I think many things should be tried, could be tried, right? The Lego GPT I mentioned, and it already generates robotic assembly instructions. I think it's several steps that need to be taken in our field. So the way with Angela and Jeve, the way we work is kind of step by step. We start with concept, then we'll add program, we'll add, slowly the various aspects. So it's maybe a slow way. Maybe you can also go at it a little bit more direct. It could be also that you directly start, okay, this is the materials, this is the machine, figure it out, right? But it might also be that it's suddenly the complexities or in computer science, the distribution, the statistical probability of a good solution emerging is so low that you kind of never end into that. So I'm in favor of this kind of slower process where we can apply the hierarchical and interdependent way of thinking in architecture that we have. So really understanding how, being kind of self-aware of how we would approach something. Because you might think, okay, give me 2 kind of sheets of material, I'll put something together. But what's really going in your mind when you think how you will put these things together is really a world, right, on its own. So that thing to be made more explicit and at the same time not encoded into this very rigid logic is where I think the potential lies, yeah. And images are low-hanging fruit, but yeah, that's where things are now. Robert.
So you talked about the incoming students, right? So I'm wondering what's going to be the most important skill that we have to teach at ETH? The ability to be eloquent when talking to the machine? Because all the crafts, the sketching, the programming is not going to be that important. Somehow we come back to the eloquence of the architects in orally selling a project.
I don't really maybe have an answer for that. I think, yeah, that's a quality that will be needed and will not go away. But the ability to critically think and assess what you have created, right? Architecture is this moment where you create and reflect at the same time. And if you have a machine create stuff for you, you're not part of that journey. You're not reflecting on what's being created. So it lacks the opportunity to reflect and discover solutions, you as a human designer, to discover solutions that might have been. I think somehow embedding that way, that I would say more conventional, more traditional way of how we work with architecture, that we create something, reflect, and by working through the problem, we actually understand the trade-offs, we understand start shaping the criteria that will help us find a good design. That is quite important. That's something that one should keep. Architecture, the press of a button is not architecture that's probably interesting or worth the world.
Regarding the quality or like the rating, would we need to go in the direction of like have measurable ratings for aesthetics or stuff like this? At some like how can we rate machine intelligence like this?
I think it's a great question. My PhD supervisor sent me a screenshot from the paper we published on the parametric models, where we say these tools are unable to apply any quantifiable criteria, but they are capable of applying qualitative comparison. Can you imagine writing a sentence in a paper like that 5 years ago? I think the qualitative comparison is also how we work, right? We see something and we formulate our own understanding of aesthetic appreciation, by example, by observing a master work or by observing someone else present to us, create with us, and we learn from that. So it's not something that, I said that at the beginning of the talk, it's not something that it can be explicitly defined upfront. We as a discipline create culture, and we create this culture not by methods, but by discourse. So this discourse needs to remain a very important aspect of the discipline as well. And embedding the AI agents in that discourse can probably be done in many interactive ways, in a very augmentive ways, that they augment the human in some semi-autonomous way, so that they challenge the human. That's part of it, but this discourse will be extremely important because it's always a moving thing, right? Architecture has evolved in the forms and in the expressions, in the programs that it produces, not only based on technology, but a lot based on culture and how society has moved.
Any further questions from the audience?
It's not a question, but it's just an observation. I'm a bit more optimistic about the future of architecture. I think it will take time to machine to replace us, which is good. Somehow I felt in the last years that architecture is becoming much more complex than what it was. But I think the challenges are exactly there to help us to reduce the crazy effort that is needed from an idea to reality, to construction. There, I feel there is so much potential, having this agent that help us to understand facades, how to make them more sustainable, structure, optimizing. This is where we need to explore. I think the cultural thinking, the special thinking, the urbanism, leave it for the humans, because I think there, I think we can still do better. And but there, from the idea to the reality, there is so much potential. So in the end, it will be a kind of joint forces between still the brain and the machine. So that's a bit what I feel today, and it's a good kind of feeling. So because I felt okay, maybe we're in a moment where really the machine can replace us. Culturally, I think it's still very far.
Yeah, I think so too. Thanks for sharing.
Great, thank you there. So I think this is about time we can start to go over for the apéro. One thing which I thought I would mention, I'm still thinking about what I think are the 3 most important slides that you presented.
Yeah, we can.
I chose I think they're around 4,
okay.
which, but we can discuss it at the apéro. So this might be an opportunity to think about what you thought might be in those top slides or points. And I know we'll have a lot to discuss in the next months moving forward. And with that, I'd like to thank you, Anton, very much for your talk. We have started to get these.
I get a bag.
Yes.
A Design++ bag, finally.
Yay. Some swag.
Yes. Thank you.
Yes, thanks. And so enjoy the apéro. We'll see you next semester. And thank you for joining tonight. Yes, enjoy the apéro.